Welcome to the panel, Thursday afternoon's panel. I am delighted to welcome the panelists. So we have, there's Avi Wigderson from the IAS, who is remotely attending and participating. Mark Braverman from Princeton, Professor Lenore Blum from Carnegie Mellon University, and Professor Madhu Sudan from Harvard University. All the panelists are, I think, we broadly in the area of theoretical computer science. So there'll be sort of the theme for the panel as well, these interactions of theoretical computer science with the rest of mathematics. So this also leads into tomorrow morning session, where most of the talks tomorrow morning will be broadly in the field of theoretical computer science. And so before we get started with the other questions of the panel, I think just for the interest of the audience, and also because I think everybody's answer to this question may not be exactly the same, let's start with what is theoretical computer science? It's a much newer area of mathematics, and it is rapidly evolving. And so let's start with just asking the panelists this question. Yes.
Okay, so recently, not so recently, Manuel Blum and I have been working on theory of consciousness from a theoretical computer science perspective. And every sentence of our paper starts out with the following, because people in consciousness science who are neuroscientists or cognitive neuroscientists, philosophers, don't know what theoretical computer science is. So this is our first sentence. May and may not be. Okay, we study consciousness from the perspective of theoretical computer science, a branch of mathematics concerned with understanding the underlying principles of computation and complexity, in particular, the implications and surprising consequences of resource limitations. That's our first sentence.
Great. Madhu, Avi, anybody? Would you like to add?
Yeah, I completely agree, of course. So generally, it studies the mathematical foundations of what computation is. This is a central concept we are trying to understand. It studies this both in computer systems, but also in computational phenomena wherever they occur, in nature, for example. Like Lenore said, we are trying to understand how different algorithms, different computations expand important resources like time or space or communication or energy or any other important resource. And it also studies properties of computation like their privacy or fairness, notions like this, or consciousness. I think that the field has been focused on the first part, on mainly understanding computing systems in their variety in the first several decades. And once we have built up complexity theory, it became easier to interact with the sciences and try to look at the computational lens of theoretical computer science on natural phenomena.
I do want to add a little bit. I mean, I think it's all sort of different people looking at an elephant and coming up with different renditions. So for me, I would think of theoretical computer science as really the subset of mathematics which is very focused on the constructive aspects. So when we deal with many mathematical questions, we may ask, does a solution exist? What does the space look like? In computer science, we will often ask, how will you find that solution, or how will you enumerate all the solutions? So there is many standard questions in mathematics get transformed by this perspective, especially in the field of, say, combinatorics or something, where there has been largely this tension between, do I really have a solution in hand or do I not? Computation often gives us the tools to say, yes, do you, or yes, you don't. And it has been a sort of a very a broad field, which has had, I think, also cast very nice lens on existing questions in mathematics.
Great.
So yeah, I think it's a pretty exhaustive list so far. So I would just add that computers and computing systems have obviously are rapidly evolving around us. And one of the other features of the field as an applied mathematics field is the commitment to keep up. So we are, wherever computing goes or takes us, we follow and try to connect it to existing mathematics, to new mathematics. So we are also an applied mathematics field, kind of helping drive and also keeping up with computing out there.
Lenore, you have
I'd like
something
to
to
add,
add?
yeah, something else. I was thinking, there's a lot of bold out-of-the-box thinking in theoretical computer science. I think that's kind of a theme. And that resource limitations matter is kind of a new concept. So, you know, theory of computation started with basically with Alan Turing in the 30s. And until the 60s, people were looking at what's decidable, what's solvable, and what's not. And in the 60s, when computers became more available, people started to realize that just because a problem was solvable, it might not be feasibly solvable. And that was so contrary to the view of mathematical logicians at that time that many of people who were looking at this early stage of complexity theory were made to feel very uncomfortable in math departments. So for example, Manuel Blum, my husband, was a assistant math professor at MIT in mathematics, left that MIT to go to the new computer science department at Berkeley. And as you know, Steve Cook here left the Berkeley math department to come to the new computer science department here. And so these people really started theoretical computer science in the computer science departments that were so open to new ideas. And the math logicians, including my own advisor, unfortunately, Gerald Sachs, was one of the key people in recursive function theory who was really down on this whole field and said you would never get tenure if you stayed in this field. So I think it was a big sea change, and it was very bold and courageous for people. And then later on, and other people can talk about this, the idea that you can create randomness, you know, that would you be in a state of sin, according to von Neumann, that you can actually generate randomness. That was another very bold idea. So I think it's a field that's been open to bold ideas.
Okay, great. So that I think it leads into my next question, which is that so maybe complexity or theoretical computer science wasn't as accepted as an area of mathematics early on, but increasingly it has become more and more relevant and accepted. And there's been a lot of synergy. There's been a lot of techniques from different areas of mathematics that have been useful for major advances in theoretical computer science. And in the other direction as well, advances or problems and techniques from theoretical computer science have had enormous impact in other areas of mathematics as well. And they have, I would like to hear from the other panelists what they think about this, about the impact of theoretical computer science in other areas of math.
Avi, do you want to go first? I think you're itching.
I can always talk, you know. Yeah, I think that related to what Madhu said earlier, there's a very natural way in which the study of computation and complexity interacts with mathematics when dealing with how difficult it is to find a solution rather than just postulate or prove that it exists. And this constructive aspect, and especially the efficiency of how simple or complicated it is to find a solution, has deepened math in almost all its areas, because often to find more efficient algorithms, you needed to develop the structural aspects of this field far more than it existed before. This was true also for decidability in the early days, to find, you know, that nothing is decidable required a new theory to the first order theory of the reals defined, you know, needed the development of a new theory and so on. So to make algorithms efficient, what we call maybe polynomial time for or other limits on resources have begot much deeper structural results in mathematics. This happened both by mathematicians and by complexity theorists. I think I can, I'm sure that people are aware of certain recent breakthroughs in mathematics that were created within computer science for their own reason. I can list a few and then let other people speak. I just want to say that they came often from very different considerations. So one of the early, in 2000, Agarwal, Kayal, and Saxena found an efficient characterization of prime numbers. This is a problem that Gauss more or less told the mathematical community that it's a disgrace that we don't have an efficient way to determine if the number is prime. And more recently, about 10 years ago, there was a resolution of the Cadison-Singer conjecture, a very important problem. You can think of it in von Neumann algebra or quantum information theory or in probability. It has many manifestations. This was done by Marcus Spielmann and Srivastava, really trying to improve some construction, what is called the sparsify of a graph, and make it absolutely optimal. There was a near optimal construction, and to make it optimal needed the development of a new theory of interlacing polynomials, and it was just for algorithmic efficiency. The more recent one, which is maybe even more surprising, is a connection of quantum interactive proofs to important problems in mathematics and in physics. This is a recent paper on MIP star equal RE by G et al. That resolved in the negative the Korn's embedding conjecture and several other conjectures. The fact that interactive proofs in general, I'll talk about them tomorrow, have anything to do with these structures is more, maybe surprising or amazing. But given that it has to do with approximating infinite objects by sequences of finite objects, is very high level, the connection. And the last, maybe in the list from a few months ago, was almost optimal bounds on three-term arithmetic progressions in the integers. This has been, the subject of serious attack by everybody, by all experts in almost a century now. It was done by Kelly and Mecca. And there the connection is, the connection existed with understanding pseudo-random properties of subsets of integers. And I think the 3 decades of study of pseudo-randomness within theoretical computer science really helped these guys make this breakthrough. I'll stop here.
Thanks, Avi. Okay, great. Anybody else who wants to add to this?
I'll add a couple of
Yes.
other examples. I think one area of math which has seen very interesting connections starting from long ago, probably Valiant's result showing that the permanent of a matrix is sharply complete, which sort of, so this is a beautiful question asked by van der Waals in the 50s earlier, where he said, if you're given a matrix, an n by n matrix, and you want to compute the permanent, what is the permanent? If you haven't seen this before, it's the determinant without the signs. Okay, so can you do this by somehow representing this matrix by a slightly larger matrix whose entries are linear forms in the entries of the original matrix? Okay, so is there some way of representing the small permanent as a determinant of a slightly larger matrix? The answer is yes, depending on how you define slightly large. If the slightly large is exponentially large, it can be done. So this is not an impossible task, but you really want to ask the question, can it be done by a polynomially larger thing? Until the advent of Valiant's result, I think this was a completely open question. Then with Valiant's result, became quite clear that this should not be doable. It would imply, among other things, that NP equals P or something along those lines. And since then, we have plunged along this question, making this the algebraic analog of NP versus P, and studying this algebraic analog. I mean, Lenore here has written the book on this subject. There have been many subsequent works, and most recently there is this geometric complexity theory, a field that has emerged with great, beautiful questions coming, in representation theory and algebraic geometry, and they're trying to understand what the answer to this question, to prove that the permanent cannot be represented as a determinant of a slightly larger matrix, has led to amazing questions, and I think it's sort of charging a lot of there's subsets of mathematicians who are sort of focusing on this question. A second field, which is probably not so clearly adopted, but I think is going to be tends to have lots of interesting correlations along the lines of the impact of pseudo-randomness. This is sort of similar, I think, is the field of property testing, which is in computer science. This is the field which says, well, I have this massive amount of data. I want to do some random sampling and try to infer some global property. Can you do it? And we have all kinds of very intriguing results saying, here's a non-trivial example of a property that can be inferred. Here's another non-trivial example. And the resulting questions and answers and their ramifications seem to be like constant in different areas of mathematics. These are more sporadic, but very often seen.
Thank you, Madhu. Mark or Lenore, or you want?
I might say some other things. So I'm going to turn the question around. So, which is really great that you're talking about applications of TCS to mathematics. So of course, mathematics has had huge applications and interactions with TCS, obviously probability theory and number theory is probably one of the biggest. But I'd like to bring up another that hasn't been so acknowledged in TCS, and it's an area I've worked in. So TCS has had a peculiar relationship with analyzing the complexity of algorithms that are intrinsically defined over like the real numbers, the reals. So, I'm thinking something like a standard thing is Newton's algorithm. You take a real number, you just use Newton's algorithms for solving equations, whatever. Anyway, so that's a very standard algorithm in numerical analysis that TCS has not really grappled with too much. It came up, I became interested in this with the linear programming problem, where the polynomial time solutions for the linear programming problem from TCS really depended on that the inputs were rational numbers. Now, mostly when people are looking at linear programming problems, they're thinking of the underlying space as the real numbers. And when you decide that you're going to take rational approximations, and TCS is the way you measure things is the number of steps dependent on the input word size. And you could take an arbitrary number of digits in the approximation and then be allowed a lot more, in your analysis, a lot more time to, especially if a problem's well conditioned, you perturb it by a little bit, you're adding lots of zeros and a one at the end, you're allowed a lot more time. It didn't make very much sense to me. And this is where actually numerical analysis comes in to talk about to influence complexity in theoretical computer science, because in numerical analysis, people look at the what's called the condition number of a problem instance. If the instance is well conditioned, you don't have to hold a lot of bits. But if the instance is very ill conditioned, you certainly have to hold a lot of bits. And that's how you can translate problems over the reals naturally into problems that make sense particularly into terms of complexity analysis. So if you have a linear program where you're looking for an optimal looks like this, that's very ill conditioned, you need a lot of bits, but it looks like that. Forget it. You don't need too many bits, especially with so-called interior point methods. And I'd like to mention also that, so this notion comes from numerical analysis. But surprisingly, actually, it goes way back to Alan Turing, a paper that he wrote in 1948. Very little, most computer scientists don't know about this paper. And he was looking at analyzing errors in looking at linear systems and solving linear systems using matrices. And he was wanting to, he had the feeling that on average, the errors didn't matter too much. And he introduced the condition number. And in fact, that result was later proved very formally by Alan Edelman at MIT, actually. So there's a kind of interesting intersection over the years of the various fields, and even Alan Turing himself, who was the initiator of the TCS, is also a little bit of initiator of this way of looking at real numbers in terms of complexity theory. Throwing that out. I know that Mark and I may have different views on this, but historically we've had, but this is my perspective.
So I would just add that in terms of impact, a lot of the things are kind of, so there's the top level things like exciting open problems that felt that Avi discussed, but there are also whole fields where it's just heavily intertwined now. So Boolean function analysis is a common utility with a lot of basic results are motivated by TCS, but used equally in other adjacent areas. Things around what Madhu talked about, the theory of polynomial circuits and connections to polynomial complexity, coding theory, that's another one where there are just a lot of connections. Of course, combinatorics and probability, which were historically connected, but probably the most useful things are the things that don't even come up anymore because it's just common utilities. But it's also, of course, exciting to see big wins and just as the field matures.
Okay, great. So, Madhu, did you have something? Look, so over time, given the connections or the impact of different areas of mathematics on TCS and the other way around, maybe it seems like it's increasingly important for beginning researchers in the field to have maybe a large breadth in mathematics. Do you think that is true? And what advice would you give maybe early researchers to focus on, or to, like, what is relevant, what is interesting background to have to start doing research in questions in theoretical computer science?
Okay, so let me jump into this one. Shubhangi did send us a list of questions and I didn't read them. So this is being answered without any preparation. But when I look at the fields of mathematics that have been very relevant to theoretical computer science and advances in theoretical computer science, I think back to the 70s. Maybe it was graph theory and combinatorics. In 80s, we saw a lot more number theory. In 90s, we saw some algebra. In 2000, it was the analysis of Boolean functions and so on. In 2010, it's a lot of actually numerical analysis and probability theory. So I feel, if you are going to go betting on any one of these fields because it's going to help you in theoretical computer science, you're probably going to get it wrong. Okay, what seems to work well for us is the openness and fearlessness, which all mathematicians should have and all theoretical computer scientists should have, which is any area of mathematics is eventually coming from the axioms. You spend some time, you immerse yourselves in the questions, and eventually learn it well enough to be able to do it. It has certainly, I don't know that I've done this successfully in multiple areas, but all the algebra that I know is self-taught, and it suffices. Sometimes you find out very new things, and sometimes you find out very old things, but they work. So that's my feeling.
Anybody else wants to say something about this?
Well, I basically agree with Madhu. All my education is as a computer scientist, so every mathematical area I felt I needed to use, I needed to to study and learn about it. I think that I was lucky throughout to have often colleagues in different mathematical fields to help with this, or to collaborate, or to teach me. And I think I agree with Madhu also that there is a certain aspect of fearlessness, of being willing to learn. This is true, of course, differently for different people. I think that the same is true for mathematicians. I believe now, like mentioning interactive proofs of all sorts, when this result MIP star equal RE, which I mentioned, which has this impact. I was talking to people in von Neumann algebras, and you know, there was a question, well, we need to learn these TCS techniques of what are these interactive proofs and multi-prover interactive proofs and quantum interactive proofs. It's all the same. I mean, you need to learn it. It's learnable. I would say that learning theoretical computer science in various parts of it is easier often than learning, you know, analysis or algebra that are needed for our problem. But collaboration happens in all, I think, great collaboration happens all over the place between us and all areas of math.
Okay, well, I think you need both depth and breadth, but I actually like to emphasize depth, particularly now I'm working in a very interdisciplinary area, and people ask me, well, consciousness science, you know, how do I get into this? My feeling is if you know some area very, very well, you really, that gives you the kind of foundation to think about other things. So I tend to go into the depth as an emphasis and bringing what you know, really are expert at. And then you can interpret other things in terms of what, so that's, I'm learning a lot of neuroscience now, which I never could do before because it just seemed like a lot of words and it's so complicated. And now I sort of hang every concept onto our model. And now I'm starting to understand things better. So I think that when you have a kind of core, it really helps a lot. And I tell also young students, like, you know, study mathematics or computer science or neuroscience or philosophy or whatever deeply, but be open. And I think this boldness is really kind of important. I think the one trouble with going into depth often is then you become very narrow-minded. And I think that's important, not to be narrow-minded.
So in terms of, since the question was advice for junior researchers, most people know what type they are, or at least that's part of the goal of your education, is to figure out, do you enjoy breadth? Do you enjoy depth? Or are you done, like once you learn something a little bit, do you want to hop to something else? Are you excited about that? Or is it a distraction from your depth? So the world is big enough that first figure out what you want to do and then find where they like it, not the other way around. You're not a big company that needs to sell many things to many people. You're just one person, and there are many different tasks and many different directions, and we need all kinds of people, and just do what you are best at. Don't worry as much about what else, what would be good in the abstract.
Okay, so thanks everyone. So let me get to my another question on my list of questions, which is, what is the impact of institutions like the Fields Institute or the IAS or the Simons Institute on the development of a field? It could be theoretical computer science, it could be just mathematics in general. What role do these institutions play and how important have they been? Does anybody?
Mark this time.
So I guess it's really important, especially in new fields where kind of so the biggest advantage of places like this is that they're much more reconfigurable. So there are constantly new events there is an ability to combine old topics with new topics, and kind of support new emergent activity in a way that, say, academic departments operate on a different time scale. It's a 30, 40-year time scale, and not on a scale of years. And in fields where things are constantly changing, it's especially important to have places like this, like fields like the Simons Institute, where it's something new and it brings new people, and there are sometimes kind of almost legendary outcomes. I think an old win was a lot of the game theory in the late 40s came out of a few kind of people getting together at the IIS. But it's completely critical because it's hard to create to support this kind of activity at scale through traditional departments.
Thanks, Mark. Does anyone want to add to this?
Totally agree with that. I think the institutes have done wonders in terms of intersection of different areas of mathematics, and also mathematics looking at other fields. So in theoretical computer science, the idea of lens on theoretical computer science lens on different area, it was actually a term I think started with Descartes. And we've looked, in the social sciences. I think AI will be a really big area, AGI, artificial general intelligence. And I was at one time deputy director of MSRI, and it was amazing how, getting different areas together and theorems would just come out all the time. I was trying to think of there were some really spectacular theorems in the 90s that came out of MSRI. Also, I noticed that, for example, here you're going to have a program that I would be very interested in coming to next year on neuroscience and mathematics. So hopefully I can apply and be accepted to that one. I just came from one at the Simons Institute, which was also on AI and psychology and neuroscience and consciousness. So I think the institutes are doing a great job in terms of looking outward and bringing math and other areas together.
I don't think I have anything to add.
Avi, do you?
No, I don't. I just think that this question can be sharpened. I don't know what the conclusion will be, which I think the NSF is debating every few years. Mathematics has many more institutes, and most of them are supported by NSF, and they are facing the critical question is to have more individual grants or to support more institutes. I think it's a very difficult question, and I think given that it's math, which is a big subject, they have to face it. We have, some program at the Institute for Advanced Study, and we have the Simons Institute, which I think is wonderful. I don't know if another one is needed, and I think it's just a tough question for the money distribution.
Great point, yeah.
Okay, great. So somewhat related, what does everyone think is the impact of big awards like the Fields Medal or the Abacus Medal or other big prizes in a field like theoretical computer science or mathematics, and how has it impacted the field?
I don't know, you want to go with this one?
Yeah, I'm going to talk about this later, right before the film. So I'm going to.
So Lenore has some very interesting thoughts on the topic.
A little
Important. I think they're important.
a little
thoughts
contrary
about
point of
this.
view.
And
I think I heard Gregory Lawler talking about the impact of these medals on fields, which I thought was very interesting. I'm going to look at a slightly contrary thing, but you have to come to the films if you want to hear what I have to say.
Avi, you want to say something?
Well, I guess I have to. Well, I always had a problem with prizes. I'm not complaining about what I got. I just had a problem because there are all these people who played similar parts in similar developments in all areas of mathematics and in theoretical computer science that are not getting the big awards. So I'm not sure that the existence of big awards is really an incentive for any particular person working in these areas, in math or theoretical computer science. I know arguments for why they are good and why they are good for the visibility of fields outside, outside themselves. But I think they sometimes create distinctions that are absolutely unnecessary.
So I won't say a lot, but I'll just say one thing. I don't have a strong opinion on this question, but another strong opinion that I am aware of and was reminded just in a break earlier today, because I was browsing the books on the Springer desk, and one of them is an edited volume by Oded Goldreich. And if you read the preface of that edited volume, it's already got a discussion about the merits of recognition and acclaim and competition and prizes on scientific thought. So I'm not going to say anything, but do go take a look at that one, and the pointer is there.
Yeah. So I was wondering, the abacus, which was the former Evelina Prize, in a way that sort of separates things, because that was set up to acknowledge information sciences, and actually computer science type of people here have gotten that award. And somehow there's the fields on the one hand from the IMU, International Math Union, and there's the abacus on the other hand so one's for mathematics, the other's for computer science. And it seems to me that that's even set up. It was like it's set up to separate the areas rather than to bring things together. So I think it's a little bit of a residue of old thinking. And it reminded me also of the MSRI. When the building was first built in Berkeley, they didn't wire it for computers, because they said that mathematicians would never use computers at all. And when I was there as deputy director, we were rewiring it for computers. And now actually it doesn't have to be so wired, because it could be just wireless. But I thought that was really kind of, again, the changes in perspectives of the different perspectives. So I would prefer somehow the abacus and fields to some, because fields is also every 4 years, and I believe it also has the 40-year limitations, which I have some problems with, but nevertheless, somehow I think they should be aligned much more.
So in terms of, it's a little bit like the question about institutes. To make it sharper, kind of, you have to look at the alternatives. So how kind of, who steers fields like sciences? So the alternatives, it's not so, it's many of the things are either kind of imposed from the outside or in consultation with us. So governments, I guess if you want to start a new institute, it's either some combination of governments, big donors. So I guess if you could also go start a big hedge fund and then make billions of dollars and start an institute. That's another way to steer math or any area of science. And awards is one way to kind of to nominate champions in some ways from within the discipline, kind of mostly by the discipline. So to get some of the autonomy back. And it does come up internally when priorities are discussed inside the university, and you're against 3 Nobel laureates. It's in a vacuum, maybe there shouldn't be Nobel Prizes either, but it would be unilateral disarmament. So that's part of the context for kind of having awards, and maybe having more awards kind of without causing too much inflation might be good for a field or subfields. It's, again, it's not, it doesn't make sense in a vacuum, and definitely I have it on good authority that mathematics doesn't need awards, like the discipline, not the human activity, the subject. But this is one thing that we can actually control more or less compared to many other things that are imposed through the outside. So
does anyone have anything to add? Okay, so I'm going to ask one last question and then I'll open it up to the audience if they have further questions. And so the question is that, okay, so like in many other areas of math as well, so TCS has many big famous open questions that have been guiding the area, but the area has also been rapidly adapting and evolving and growing. So how do you see the area evolving over the next few decades? Like which direction will become the focus, or just it's an open-ended question, just where do you see the area going?
Well, I expect that we will see a lot more interactions with other sciences. I believe that computation as part of models of natural phenomena in biology, in chemistry, in physics, in the social sciences, in economics, will be adopted in, it's already being adopted in some parts, like brain science, neuroscience, and biology. I feel that we are going to see algorithmic thinking entering curriculum of basic courses in these sciences, and probably there'll be the invasion of the other direction, where we'll see a lot more, at least at some level, courses on the natural sciences and their way of modeling phenomena. And this combination, I believe, will be very powerful. On our internal open problems, we are making great strides, but the really big problem, which is finding a single heart function, something that we cannot do in linear time, we are stuck big time. I wish there would be some progress on this, but so far we aren't there yet, despite decades of work.
Anybody else? Mark?
Okay, I'm going to follow up what Avi said on interdisciplinary. And I think that's where mathematics and TCS has a lot to offer. Because in many of these other fields, there are notions that are generally accepted, but they're informal, they're vague. And I think what mathematics does and TCS does is it makes formal definitions and formal maybe axioms, and then you can see what you can get from that. And then a big question is, how do you, especially if you're working in, for example, neuroscience or this area that we're working on, how do you verify that what your model is doing really aligns with what people in the field are thinking about? So, but I think by getting very, mathematics, you always want to have a minimal model, the fewest things that will explain the most, rather than in many of these fields, they're giving you so many things, and maybe just to cull out the key ideas. And I think that's what math and theoretical computer science can offer, but it has to also speak to the field as well. So it's got to align as well with, in our area, there's a guy called Kevin Mitchell, is a neuroscientist, and he just published 16 questions that any theory of consciousness should answer, which was great for us because we could go through our model and see how our model was addressing his questions, which was really a gift to us, because this is coming from that field. And I think when you interact with people in other fields, so I think the contribution of the math theory is really to get formal definitions, key ideas, and then work to see how your ideas really align and can do predictions and explanations. But yeah.
So I hope that nothing that we can guess will be on the list. So one of the strengths of theoretical computer science is that it's kind of creative destruction. Problems usually don't stay important because they're old, unless they're still important. So P versus NP is not important because it's old. You could erase everything and we'll be back at it after 6 months. Probably it wouldn't take like last time, it wouldn't take 30 or 40 years of logic to discover it. We would try to do something with a computer and discover it very quickly, maybe in some other language. So hopefully nothing that we care about, just because I hope that if they still care about stuff because we care about it, I hope they don't, something went wrong with the field. So hopefully it's new things that we can't guess now.
Maybe I can add a word, continuing what Lenore said. I think that we in TCS developed a very powerful language and a very powerful methodology for modeling computational phenomena. And because almost any process you can imagine is really an information process, it is computational almost by definition of what the process is, what the natural process is. It does various simple atomic operations again and again, and it creates, various wonders that we see around us. I think that this methodology that as we are obsessed with classification of groups of problems of a similar type. In many sciences, different problems are studied individually. We are obsessed about reductions, about the relations between problems that we may not understand either, but we can see that solving one helps solve the other. I think this and various other parts of this methodology, this language and point of view are going to be extremely useful.
Good. Thanks, Avi. So I've exhausted the list of questions. Yes, questions from the audience? Yes, good. I will.
Thank you very much. I mean, my question maybe will be a bit provocative. So I was hearing you, and my impression is that you are guys mathematicians. You are part of us. So my question is basically, what is the standing of your discipline among computer scientists?
Oh, wow, okay.
And the reason I'm asking, because say in such area like biology, theoretical biology became kind of a bad word because nobody is interested anymore because they're so much excited of what they're doing in their labs that they don't have interest in this anymore. So I'm asking whether you guys appreciate it in other parts of computer science, like HCI or like machine learning or graphics or robotics or whatever. Because I had experience talking with other computer scientists and I didn't have feeling that we are the same discipline, but with you, it sounds like you mathematicians. But that's my question.
So I can go for that. I mean, I remember about 30, 40 years ago when I first entered academia, I used to feel that there was a big gap between theoretical computer science and the rest of the computer scientists. And there were definitely eras where we saw a lot of tension. I think we've completely grown out of it now. I have the sense that everybody in computer science, everybody in my department understands not the finer details of what we are doing, but they know algorithms, they know efficiency, they probably know P versus NP. They understand that there are the next steps which they may not understand, and hence we'll leave it to you to deal with your problems. But every once in a while, there is an interaction and it comes back to them. When I was working in the late 90s, I encountered this idea like list decoding or something. 10 years later, 20 years later, it entered some networking environments and they were playing with the same concepts, not using the same tools, but the same definitions. And then they realized, oh, you were talking about this. Then now we're doing the same thing. So they understand this. And I feel that a lot of it is coming up because the early generations of computer scientists did not have a computer science training. And if they came from they were working in different areas, they had completely different backgrounds. Now, many of them have seen a computer science undergraduate program with many similar elements. They understand and appreciate the problems. And just like I would not want to code something on a computer tomorrow because I dread programming, the others dread proving theorems. And so we respect each other's dread.
I would add that it's a little hard to answer this because computer science as a discipline has been expanding at a very fast rate. So in some sense, as a fraction of computer science, maybe we are diminishing just because the median computer scientist is somewhere in Apple working on a self-driving car or something. But somehow even within academic department, because there is also academia as a small part of computer science, I think our share has been steady, or standing has been steady or slightly improving. Of course, this comes at the cost of paying attention. So I think it's true much more so than, so a math discipline probably, if it decided to insulate it from the rest, would survive 50 years. We wouldn't before, or maybe longer, kind of just on saying we are working on hard, old, important problems. In computer science, this doesn't have as much currency. But as long as you're willing to talk to people and listen and care about computation as it evolves, it's been steady or improving even. And we're building more bridges to economics now, to kind of the only thing I would say that okay, I don't know how controversial, maybe it's nobody cares in this room, but the only part of blockchain that's not a scam is basically either cryptography or theoretical computer science. And universities realize that, right? They don't want to be a part of a scam. So it's a big area now. What are they gonna do? They create more shared theory essentially. So yeah, so there are a lot of new opportunities as long as we kind of are willing to engage as a field, and there are interesting problems there. It's not like selling out, it's actually interesting problems. The field is doing well.
Well, I think I found both your answers somewhat optimistic. I think that we've gone a long way since 30 or 40 years ago, no doubt about it. I think the respect to theory within computer science has increased dramatically, but we have a burden that somehow, like Mark said, mathematicians don't share, because working on a hard-old problem in mathematics and making small progress, because small progress is almost all we do most of the time until some breakthrough occurs, is completely respected by the rest of academia within mathematics. Whereas within computer science, the many little things we do, the little papers we write every year, I don't think they are, this kind of activity, I agree with Mark, will not be tolerated a long time. I think we have more respect to gain, more recognition of these ideas that came, like you mentioned, in blockchain technology that came from crypto and interactive proofs. In fact, the existence of the internet owes everything to the development of theoretical cryptography in the 80s, which of course has to be developed before the internet. And of course, the existence of computers will not happen without Turing having first a theoretical model, and then von Neumann, and then others to do it. But I think that some parts in the general computer science academic world are aware of this and respect this, and hires out of academia people to go to industry. And there are others that know less or appreciate less. So we have, in my opinion, quite a ways to go.
I'd like to go back to the very first question, which was, I think it was defining what is theoretical computer science. And I think you all said roughly that it's a discipline which concerns itself with the question. It's not enough to know that something exists, you have to know how to find it. There's actually a small sub-branch of mathematical logic called constructive mathematics, which concerned itself with precisely that question. That is, it's not enough to say that something exists, you have to say how to get it, but not necessarily, or have an algorithm for finding it. would you say that theoretical computer science has subsumed the area of constructive mathematics?
So I think what's missing there is resource limitations. You can have constructive methods that are infeasible, actually. And I think that's a really big, so I think the real intrinsic change with the thinking with theoretical computer science is the feasibility. And to go back to the question of how the rest of the computer scientists are viewing us, if you think about the logicians who kicked us out or kicked people out, many of them are central to looking at, oh, this great problem, does P equal NP? What is that? Is that decidable? Is not how we can think. So in fact, it is a kind of central problem, and it's one of the clay problems. And so even the people who rejected it as an important problem I think, have understood how important it is. So, yeah. But I think the big difference is they're related. Yes, of course, algorithms and constructive, but resource limitations, time, space are really critical for theoretical computer science.
This is a different, sort of more practical thing from being a professor who talks to undergraduates. I'm in the mathematics department. I often have a student come in who's interested in the exciting work in AI, ML, all your other abbreviations, but wants to be a mathematician on the mathematical side. I'm sometimes not sure exactly how to advise that student. What should they be doing in graduate work? Where should they be doing? Where should they be looking if that's their vague interest?
Anybody have a?
Well, I don't think there is an easy answer to this, but one can look around at work done in what may be called theoretical AI in some of the both theory conferences and some of the AI conferences, and those on the border. They are like with any field, AI also took the attention of some extremely great theoreticians who work on various parts of AI, work on safety, work on the limitations of what deep networks can learn and what they cannot. The variety of areas where it's really, I think of AI, the current AI, as a natural science. There is this animal we discovered, and it can do all sorts of things. In fact, it can do lots of things that are very unexpected, and we are trying to understand it. And we can understand it in natural science tools, run experiments, simulations, architecture changes, and so on. We are very lucky that this animal is not protected by any rights that real animals are protected. We can chop off its, legs and hands and layers and so on, subject them to various experiments. And we can also try to theoretically model this. All of these things are being done, but of course we are still in the baby stage of understanding. So I don't know about the graduate student. I think that they will need to, if they want to do mathematical work, they need to consult an expert who is doing some kind of theory. And there are various kinds to know where to. I certainly would not be able to advise them. I would send them to some friends.
I would just say that, you were asking about undergraduates specifically, right? And I think to the extent that there is some soundness and some mathematics that they can try to learn, it's basically algorithmics and statistics. And you should definitely sort of encourage them to make sure that they get, on sound basis of at least being able to express what is being done, even if they cannot understand what is being done, and how it's done. And I can imagine that, out of this, just like I was suggesting, this is a beast we are all studying. Somewhere out there, an interesting exploration will reveal insights which are mathematical, and it could come from anybody out there.
Also, you're at Chicago. It has a great computer science department and also TTIC. And you can encourage your student to take some courses in one of those places. I even have a good connection with TTIC. My son is the chief academic officer, so I can get your student in. But the resources right on your own campus to explore.
I have a question. You brought up many sociological aspects. I have a view. I might be excommunicated from here, so I will withhold those things. Let me go to your a point about consciousness. I don't know what you mean by consciousness. When you said this thing, it's a very complicated word with multiple layers of meaning. So for example, as Noam Chomsky rightly said, with all this AI hoopla, essentially paraded by capitalist media. I'm sorry, I'm not Marxist, but I'm just saying. He said, when a child learns a language, he doesn't have a million set of data or a billion set of data from which it's seeking these things. It is a very small set, a sample of information from which it creates language because of how human consciousness is directed. So when you say about consciousness and computer science, it's a very different kind of a thing than what we as human beings are organically develop.
I see where you're going. But I mean, this is exactly where we're using theoretical computer science. We're making a model, which we call the conscious Turing machine. And we're very inspired by Turing's very simple but powerful model of computation. So Turing, if you look at a Turing machine, totally simple, doesn't look like a supercomputer or anything, but whatever you can compute on a supercomputer, you can compute in the Turing machine. You can't get your head around the cloud, but you can get your head around a Turing machine. And it's really telling you about the essence of computation. So we're motivated to design a very simple model for consciousness. We have a model that where we make definitions of what's consciousness in this model. We look at the two kinds of consciousness that most of the people in consciousness, what's called access consciousness, something that's known to be very functional, very computational, and something that seems very much more mysterious. The subjective aspect, phenomenological consciousness, and we see how we can have a computational model of that as well. So we are looking at these things, and they do jibe with a number of the theories of people in the field. So you can start to look at this, and you can see what's working and what's not working. And so once you start to formulate a model, which we're inspired by TCS to do, you can start asking those questions. Does it make sense? Does it agree with your theory? And I'm very happy to talk to you sometime about our theory and see where we might align or not to that. But that's exactly what we're doing. And that's what I think the power of TCS is that you can start to make a model. And you use Occam's razor, like you want to get simple, but no simpler, like Einstein says. You want to get very simple, but you want it to be explain a lot, to be fairly powerful. And that's our way of going into this. Yeah.
Okay, I think Kumar gets one more question.
So since we are running out of time, it's not really a question, but I just wanted to end on this one note to resonate with something all of you said. We are, eventually maybe we'll see a rearrangement, a reorganization, but right now we're at a kind of frontier with mathematics and computer science, and that's going to grow and become more significant. And TCS holds a special role in promoting that, making that happen. But the institutes also play a special role, as all of you have observed. We are much more flexible in terms of the way we organize events. You mentioned that we have a neuroscience program coming up. We have an oncology program going on right now. And sometimes the impediment to making progress on a problem is ignorance. We just don't know there is such a problem. And I can see that this kind of interaction can be really beneficial in firstly letting everyone know on both sides that there is such a problem, that there isn't such an opportunity, and then bring only those who are interested together to sort of work on it. So I'm quite hopeful actually about increasing these interactions to accelerate the progress of knowledge that will benefit both sides.
If I can just sort of quickly add to that, I mean, I think TCS and mathematics are not just touching each other a lot, they're even overlapping a lot. And in particular, we have Shubhangi here, for example, who's sort of 50% in computer science and math departments, and there are a few such people around the world. And I think it's great that we are seeing more and more cross-disciplinary hires, cross-disciplinary positions.
All right, I think we have to stop there. So let's thank Shubhangi and all the panelists again.